obtain this expression. To begin, one way to create a sphere would be to graph the circle x square plus y square equals r square on the xy coordinate plane and then rotate the circle about the x-axis. After the rotation, we have a sphere with radius r. Now to determine the volume of the sphere, we can think of making vertical slices of the sphere, which vertical slice would be a disk or right circular cylinder. The volume of a right circular cylinder is pi r squared h, and for this disk, a right circular cylinder, the radius is y and the height would be from a small change in x represented by delta x or differential x. So the volume of one disk for one slice of the sphere equals pi y squared dx. From here, as the number of slices approaches infinity or the number of disk approaches infinity, the sum of the volumes of the disk or the right circular cylinder will approach the volume of the sphere, which can be seen here.
I'm going to explain you why the derivative or the rate of the change of the volume for a sphere is equal to its surface area. Let's start by describing some basic terminology. dV describes the change in the volume, dr describes the change in the radius, and dV upon dr gives us the rate of change in the volume with respect to the radius. Now let's begin with considering a sphere of radius r, and then we're going to increase it by a small amount, that's dr. And after this, if we calculate the volume of the small ring or the extra layer that's formed around the sphere, then we're gonna then we could determine the dV given a small change in the radius. So if we flatten the shell or the layer created by the increase in radius, it's going to produce a right circular cylinder as shown. And for this, we're going to squish the ball, which might look something as like this squished ball, the one that's oblique right here in the center. And we're going to eventually obtain a cylinder with a height equal to 2dr and the area of the base equal to 2 pi r square. And after this, to find out the volume of the cylinder obtained, we're going to just multiply the area of the base along with its height, that's 2dr, and the area of the base, that's 2 pi r square. Now if we go back to the first picture, we find out that the volume of this right circular cylinder right here, which represents dV, is equal to 2 pi r square dr, and therefore we can say that dV, as it's written here, dV is equal to 4 pi r square dot dr, and if we take the dr term to the other side, it represents the rate of change of volume with respect to radius, that's going to be equal to 4 pi r square, and we know that the rate of change of volume with respect to radius gives us the surface area, and thus the formula of 4 pi r square for the surface area. Hence, the derivative of the volume of the sphere is the surface area. Increasing the radius will also result in increasing the volume proportional to the surface area.
Does the relation hold in higher dimensions? To find this out, I started searching the internet profoundly and stumbled upon something called the curse of dimensionality, which roughly states that as the number of spatial dimensions go up, finding things or measuring their size and shape gets harder. As I dive deep into the research, I found out about the ball in a box phenomenon, which says that if you put an n-dimensional ball in an n-dimensional cube just large enough to receive it, the fraction of the cube's volume occupied by the ball falls dramatically as n increases. After studying the phenomenon in detail, I was able to find out the following results about the volume of a ball in 1, 2, and 3 dimensions. On the basis of these three data points, it appears that the ball fills a smaller and smaller fraction of the cube as n increases. There is a simple intuitive argument suggesting that the trend will continue. So this led me to the page titled Deriving the Volume of an N Ball. Near the top of that page was the formula as sought. I noted immediately that the values for 1, 2, and 3 dimensions agreed with the results I already knew. Beyond the fifth dimension, the volume of a unit n ball decreases as n increases. I tried a few larger values of n, finding the volume of ball in the 20th dimension, which is about 0.0258, and in 100th dimension, which is in the neighborhood of 10 to the power minus 40. Thus, it looked very much like the nth ball dwindles away to nothing as n approaches infinity, and the relation doesn't hold true in higher dimensions. Thank you all for watching the video. I hope you all liked it and got to learn something new from it.
Oh, thank you. Good research. Yes. So I noticed that 4 of you have